Hello. In this lecture, we are going to talk about obtaining extremely short pulses of light. And the way that is achieved is through this idea called mode locking. So what we have here is, so unlike in Q switching, where you introduced extra loss in the system so as to decrease the quality factor of the cavity, and then in a controllable manner switch the quality factor so as to create a giant pulse within that short time duration and then switch it back again. So in the duration when the quality factor is low, what would happen is that the population inversion would build up because the pumping is always on, uh, and the lasing will not begin simply because there is no feedback. So what is happening is you're shifting the levels of the gain threshold because the gain has to become equal to gain threshold for the lasing to begin. The gain threshold is always a little bit higher than the gain. And the moment you switch the quality factor of the cavity, what you have is a large gain, which is much above now the switched gain threshold, right? So that was the idea in Q switching. And Q switching can at most be used to get pulses of the duration limited to roughly about nanoseconds, because that is the time scale at which you can switch the quality factor. You also know that if you switch electronically, the best you can get is again nanoseconds. There is a time scale of switching for most electronics. So if I want to do better than this, one needs to actually address this fundamental issue, which is if I have a narrow band pulse in time, I invariably will need to involve a broad band pulse in spectrum, right? So in the frequency space, it has to be broad. Only then one can actually generate a narrow band pulse. So we take that idea a little further and see what are the conditions required for us to create a narrow band pulse in time. So what we will do is we'll go through a very general arguments based on locking of phases of oscillators of different frequencies. We come up with some expressions and we will see that we'll be able to map this problem of coupled oscillators which are locked in phase to that of the laser that we already have. And you see, there'll be a one-to-one correspondence between the two. Let us see how these arguments go forward. So what I'm considering now is a set of phase locked oscillators. So to begin with, what I have is I have n oscillators, capital N. I'm indicating every oscillator with a subscript small n. So this small n runs from 1 to n, right? So my individual oscillators have got the same amplitude. They have a frequency which has got an index n plus a phase which is phi naught, right? These are n independent oscillators. So what I want to do is I want to look at the superposition or the sum of all these oscillators. Let me call that sum as capital X of t. And essentially this is simply the sum over these xn's, which is functions of t. And I can simply write this in a symmetric manner, just for ease. I am taking my sum from minus n minus 1 by 2 to plus n minus 1 by 2. This also includes the fact that I'm going through the 0. Okay, so that's why there is n minus 1. So essentially I have n oscillators and I have x naught sine omega nt plus phi naught. So that is what I am looking at. Moreover, I have a relationship between the frequencies of these oscillators, that my nth oscillator is essentially, there is a central frequency, there is a frequency omega naught, and to that I add integer times a difference frequency delta, right? And my n here, so my small n goes from essentially minus n minus 1 by 2, right, all the way to minus 1, 0, 1, and n minus 1 by 2, the positive, right? So essentially I have capital N oscillators. And so you see, if you look at the spectrum, I have omega naught and I have got equal, I got another oscillator and a series of such oscillators which are separated by these are separated. So this is my frequency space. These are separated by capital delta, right, which is equivalent, right? And this corresponds to, for example, the n equal to 0. That is where I get this. Here is omega naught plus delta, omega naught plus 2 delta, and so on. And on my left, I have omega naught minus delta, omega naught minus 2 delta, and so on. Right, this is my frequency spectrum. Each of the oscillators are of equal amplitude because they all have the amplitude which is x naught, right? And I have assumed something more, that they do have the same phase phi naught, which is a fixed quantity. So all of them, imagine at time t equal to 0, they all begin equally with the same phase, right? So that is what is happening in time. All right. So now that you have something like this, let us try and do this sum carefully. So I'm just going to do some algebra now. So x of t, I can think of it in the following manner. Again, this is sum over my little n. I have x naught, and I can think of the sign as arising from the imaginary part of exponential I omega n t plus phi naught, right? Which is indeed true. So what I'm doing is I'm rewriting this above sum in this manner, where I have appropriately placed my summation at the right location, which is here. So the only thing that is n dependent is not the amplitude, which has been taken out, not the central frequency, and not the phase, but only the difference in frequency. So that is exponential I n times delta times t, right? So this is how I can rewrite this sum. And you see, let me do a small aside. You see that this essentially becomes a sort of a geometric series. Specifically, I can write the following, that if I have sum of minus n minus 1 by 2 to plus n minus 1 by 2, if I have a sum of exponential I times n times y could be any number, then you see that this I can write it down in the following manner. I can rewrite my summation index. I can change my dummy variable from small n to small m. So imagine my small m is n plus n by 2, right? Rewrite this as sum of from m equal to 0 to capital N. And now I have exponential I m y, right, coming from there. And I have exponential minus I n by 2 times y, right? This is just by recognizing that I am shifting my indices starting from 0 to n. And this I can rewrite in the following fashion. Remember that the summation doesn't care about this capital N term. So this can be written as minus I n by 2 times y. And I can simply sum this from 0 to capital N as simply exponential I times y whole to the power of m, right? Which is precisely the same quantity. And you know that this is a geometric sum, which I can simply write as 1 minus, so this is exponential minus I n by 2 times y. This is a prefactor, and I have to simply write down the sum for it, which is going to be 1 minus exponential iy, that is 1 minus x to the power of n plus 1 divided by 1 minus exponential iy, right? So this is going to be the sum of this geometric series, right? So this I can rearrange a little bit and I get the following form. Let me keep this exponential I n by 2 as it is and rewrite this in the following fashion, which is I am taking out exponential I capital N plus 1 by 2, right, as common out. So what I would get on the top is exponential minus I n plus 1 by 2 times y minus exponential plus I times y. You see where I'm going, and similarly I take exponential I y by 2 as common from the denominator, and in the denominator I would have got exponential minus I y by 2 and again exponential plus I y by 2, right? So this takes care of exactly the same thing. You can clearly see that I can write this out in the following fashion. One thing you can see that this whole term is just comes out to be 1, right? So essentially what I get here in these brackets is the remnant, which is sine with the argument which is n plus 1 by 2 times y divided by sine y by 2, right? So this is essentially this sum. So I can use this fact and then quickly identify that my y, if I replace it by delta times t, you would see, right? These are product. If I identify this, I can simply write down, let me call this equation number 1, right? I can write down this sum in the following form. So equation 1 using this relation number 2, right, results in the following form, that my capital X of t is simply x naught. There is imaginary part which is sine omega naught t plus phi naught, and then there is the one which is coming from the sum, which is n times. Uh, so remember that y is delta t, so I can write this as delta t by 2 divided by, this is sine delta t by 2, right? So this is essentially what is the sum, and we will see that we can combine these together, because you see the variation of the arguments. So if you look at this term, the variation of the argument is going like 2 pi by omega naught, whereas here the variations is going in terms of the difference frequency, which is delta. So delta is scale of variation. So all this part which I have put together, I identify this as my new amplitude, that is x naught times a. This only depends on the total number of oscillators which I have, which is capital N, and this is simply sine omega naught t plus phi naught, right? So let's look at now the properties of a n of t, right? So a n of t has a capital N of t, because that depends only on the total number of oscillators. That you would see is simply this ratio, which is sine capital N delta t by 2 divided by sine delta times t by 2. you can see that this function is going to peak every time you see that when the limit of delta t by 2, when this is a multiple of pi, right? So that is when delta t by 2 is some multiple integer multiple of pi, right? Integer values, from let's say 0 to infinity, 1, 2, 3, and so on. So you see that every time this is a integer multiple of pi, you're going to get a 0 here, and then one needs to take carefully the limit of essentially these sine functions going to 0, and you will get you can do this limit carefully, and you will see that the maximum, so the maximas lie when there's a minimas at the in the denominator. So you see that my a n t max is actually capital N. So again, let me be careful. My m can take values which is 0, plus minus 1, plus minus 2, and so on, right? So essentially the times at which these peaks occur, these peaks occur at the times which are simply m times 2 pi by delta, right? So these are the times at which the peaks will happen, and so this is the period between this capital T is the is the time period which is 2 pi by delta wherein these multiple peaks happen. So let me plot a few curves to give you a pictorial view of this, which is very interesting. So essentially what I have got, so this is my time axis, or let me put it this way, let me take this as delta times t by pi, right? In that case, you see, I'm talking about, let's say 0, 1, 2, 3, and so on, right? And you see that at this is the kind of I would get, and so on. This is when, so let's say for n equal to 3, I have something like that. So this is my capital X of t, right? So you see that, let's say I increase my n now from n equal to, let's say 3, I'm going to n equal to, let's say 7. So you see that the the kind of curves that I'm going to get is something of this kind. I would urge you to try and do these calculations and plot it for yourself and convince yourself that this is indeed true. And this is peaking at 2, right? And so on and so forth. So you see that um, the following is true. So what is happening is, so there is a width to the sharp peak. This width is given by 2 pi by capital N delta, right? So in our case, this is simply 2 pi by 7 delta, because this curve, which so I should be careful. My previous curve was for n equal to 3, but this one which I have plotted here, the one which I have just plotted, this is for n equal to 7, right? So, so you can clearly see that my pulse is and the height of my pulse, right? If this is, so let me indicate that. So let's say this was 1, 2, 3, 4, 5, 6, 7. So this would be 3, right? That would be the height, and this would be 7. That would be the height there. So you can clearly see The following, there is a periodic pulse which is coming in at a period of 2 pi by delta. So capital T is my separation between the pulse, right? So this is capital T, right? And this is simply coming at 2 pi by delta. And now if you look at the duration of the pulse, right, tau n, so this is what I call as tau n, right? This duration of the pulse is actually 2 pi by n delta, right? So this is coming at the time by the number of oscillators that you have managed to put together. So this t by n becomes my the duration of the pulse, and at the same time the amplitude of x of t, it is capital N times x naught. These are the main results, that my a n of t is sharply peaked. Second point, that my width of the peak, right? It is it Width of the peak goes like 1 over n, right? In our case, it is this t by n. Not just that, for n oscillators, the amplitude amplitude is simply n times the amplitude of individual oscillators, right? And you see that these pulses come out periodically. Uh, so there is a periodic, repetition of the pulses, repetition rate, right, which is determined periodic repetition, right? Rate will be 1 over t, and this periodic repetition is at time capital T, which is simply 2 pi by delta, right? So these are the features that we have. So the most important lessons which I want you to take from this analysis is the following, that my width of the pulse goes like 1 over n. The more the number of modes, right, or the more the number of oscillators which I can combine together and sum them up, that would lead to a smaller and smaller width. Not just that, its amplitude will correspondingly increase. And of course, I will get these pulses periodically. So where is the catch? The catch is in this fact that I should have the ability to now prepare essentially capital N number of oscillators, all having a frequency that is periodically spaced, and all of them such a way that their phases are identical, right? So these are the two conditions that I need to satisfy. You will see that even if the phases are shifted, in the sense that, imagine that, this is just an aside, imagine that my phi, it was phi naught, rather than phi naught I have phi n, where you see that if the difference between the phases is the same, that is my phi n plus 1 minus phi n, if this is some constant alpha, even then you'll be able to couple uh, these oscillators. So it is this preparation which is of paramount importance, right? Having a periodic arrangement of oscillators with the period which is there, plus their phases, phase difference between them is either constant, and that constant could be zero, so they could all be in phase. So that, once you are able to achieve that, you will see that you'll be able to create this extremely short bursts of pulses of light, which will be narrow depending on how many oscillators or modes you're able to couple, and they also will be sharply peaked, because what you're taking is you're taking energy in time and compressing it into a very short duration, which is decided by this frequency difference, which is capital delta, right? So this is essentially the main lesson from here. So now let us see how do we map this problem to our laser problem? Remember that in lasers, what you have, you're already gifted with n identical modes, right? So in a laser, you see that there are my longitudinal modes, nu m, which is simply integer times c by 2l. In this language of phase oscillators, I essentially have n equispaced uh, modes, each one separated by c by 2l. So clearly, you see that the difference in the frequencies between two neighboring modes is clearly c by 2l. That would mean that my angular frequency delta, which is what I have used on the top, is simply 2 pi times c by 2l, right? That basically gives me pi times c by l as my angular frequency difference between the various modes. So what we will get is, if I utilize these modes and lock them in some manner, we will talk about how to lock them later. But if I'm able to lock their phases, then you see I'll get a train of pulses, right? These train of pulses will come at an interval capital T, which is simply 2 pi by delta, which for us is simply 2L by C. And you do realize what is happening. 2L is the round trip length within the cavity, and essentially, the pulse is coming out after every round trip. So let's keep that thought in mind. That is my capital T. Not just that, the duration of the pulse is simply capital T by the number of modes that I have managed to lock together. And this, by the way, is going to be 2 pi times n times delta, which can also be written down in the fashion of 2L by capital N C. The question one is asking is, what is n? What is the number of modes that you have managed to lock? So clearly, you see that moment I have a distribution of frequencies, I also have a gain curve. And you see that typically, if this is the width of my gain curve, that would imply, so my let delta nu g be the width of the gain curve, that would imply that I have a finite set of modes which can be logged, only the ones that fall within the gain curve, right? Only these are the modes that are relevant, which I can in principle lock. So you see that clearly. So you see the number of modes that I can lock is simply the following. It is simply delta nu g divided by the spacing between the modes, which is c by 2l. So now let's take this argument further. That simply tells me that my number of modes is simply 2l by c times delta nu gain. So now that we have something like that, let us figure out what is my duration of the pulse. So what is the tau minimum? This is my pulse duration. This tau minimum is indeed 2L by C times the number of modes, which, by the way, we just figured out is 2L by C times C by 2L times 1 over delta nu G. So which is simply 1 over delta nu gain. So this is a very important lesson that we have learned. What it tells me is that the shortest duration of the pulse possible through mode locking is simply the reciprocal of the gain bandwidth, right? So, for example, if I have a helium neon laser, my gain bandwidth is 1500 megahertz, right? Or 1700 megahertz. So you see the minimum I can get is only about nanoseconds, right? For example, in Ruby laser, my gain bandwidth is it's broader. So I have about 10 power of 11 per second. So you see that the minimum I can get a a sub picosecond kind of a pulse. At the end, what we are going to be limited by is basically this gain bandwidth, which is there. The larger the gain bandwidth, the shorter the pulse that we can construct out of mode locking. And you see that the workhorse of really short pulses is the titanium sapphire laser, where you essentially you have a gain bandwidth of the order of 10 to the power of 14, and hence one can generate from them the femtosecond pulse out of the mechanism of mode locking. So that in effect really captures, that idea of how does one obtain a short pulse through mode locking. And what I'm going to do is I'm going to look at a few simple mechanisms of achieving this mode locking. Of course, my analysis is going to be semi-quantitative, but you will get the idea of what exactly we are trying to